let's look at an example and see how things go. We'll take it from there. We have let me draw it here. This is y, this is x. We have an area in this shape. And there is a circle in the middle of it. Let me see if I can actually move it to the middle. Maybe it looks more to the middle. Here is a line passing through this, and this is your area. So basically you have a rectangle with a circle cut out in the middle. You do have the dimensions, this side, or let me do it in two parts, this side, and let's go for the radius here. So this is these dimensions. I have to take a look. My notes. This is 100 millimeters. This is 75 millimeters. This is 75 millimeters. And the radius here is 25 millimeters. All right. I want to find the moment of inertia for this area, right, about x-axis, let's say. So find the moment of inertia. Let me just go with moment of inertia instead of saying area. Find the moment of inertia about x-axis for this area. That's just stating the obvious. All right. So we want to find the area moment of inertia for this axis, which is a composite area, using this table. Right? We know the area moment of inertia for simple shapes. All right, so here's what I do. I say this area can be formed by a rectangle minus a circle in the middle, right? So this area is basically a rectangle minus a circle. Yep, didn't work the way I wanted. Minus a circle. So this minus this. Let me do it in a better way. Move things around. This would be a rectangle. This would be circle. So later on, when you look at it, this minus this, maybe I should do it this way, is equal to this. Right, this let me put the axes. Axes are the same for both. Move this up a little bit, so I have room to put the axes there. Here we have the axes. This is x and y. This is y and x. All right, then you'll get this. All right. So I'm going to find the area moment of inertia for this rectangle, find the area moment of inertia for this circle about these axes. subtract the circle from triangle, subtract the circle from rectangle, and then find the area moment of inertia for, that would be the area moment of inertia for this composite area. All right, that's a general story. So put here, subtracting the circle from the rectangle. That's what I'm doing. Now that's where parallel axis theorem comes into play. We have this circle. We know its radius. It's 25. Millimeters. Let's go to the table here. I'm clean this up. So here is my information I have about the circle. What do I know about the circle? I know the moments of inertia about its center. I know Ix bar and Iy bar. In this case, I'm only looking for the area moment of inertia about x-axis. So I only care about Ix bar. So for the circle, Ix bar, let's call it prime. I'm going to put the center in the middle and call it prime. This is the center passing through the center, area moment of center of the circle. This axis passing through that. X prime, Y prime. So Ix prime, just don't be deceived. This is the set of axes passing through the center. Right? So I know the area moment of inertia about the axis passing through the center of the circle. Now, in this table, they're representing it with X and Y. But remember, here we have X and Y, the main axis. So I have to represent it with something different so things don't get messed up. I just represent them by X prime and Y prime. And I put Ix prime bar, meaning that area moment of inertia about axis X passing through the center. And that is given in the table as 1/4 pi R4. And R is 25 millimeters. So this becomes 1/4 pi 25 millimeters raised to 4. You can actually get that value. That will be, if you do this math, you will get 36,796.16 mm4. Right. That is the area moment of inertia or moment of inertia about axis passing through the center of this circle. Now, similar to the way we're calculating the centroids, where centroids are, everything should be in the same, should be written for the same axis, set of axes. Here we have X, Y. So that's where the parallel axis theorem comes into play. Now you know the area moment of inertia about X prime for this circle. Let me separate these. That's not what we want to do. This is circle. So I have to use parallel axis theorem, knowing this distance. This distance here, which is my dy. I can find the area moment of inertia about x, which is what I want. Ix is equal to Ix prime bar plus a dy squared. Right. Here we have a, and the area of a circle. Well, we have pi r squared would be pi 25 squared. Dy is 75 millimeters. So Ix is Ix prime What I have there, 36,796.16 plus area, which is, I'll just put it here, pi 25 squared times dy squared, 75 squared. If you do this math, you will get 11.35 times 10 to 6 mm4. And one important note, when you're calculating area moment of inertia or moment of inertia for some area, if the dimensions are given in a specific unit, let's say millimeter, keep everything in millimeter. If they're given in meter, keep everything in meter. If you use meter and start rounding the numbers, you lose a lot of accuracy. Since this is length raised to 4, you need some accuracy in your numbers. So if the dimensions are given in millimeter, keep everything in millimeter. Do all the calculation in millimeter. If dimensions are given in centimeter, keep everything in centimeter. Do not convert the unit to meter or centimeter. Then you're going to end up rounding things up. And since we are raising things to 4, just numbers are going to be way off. All right. Just put it as a note somewhere. So this is for the circle. This is the moment of inertia about x-axis for this circle. Now I have to find the moment of inertia about x-axis for this rectangle. Right? If this is the center of this rectangle, for this you don't even need to use rectangle. For this you don't even need to use parallel axis theorem, because in the table you are given the area moment of inertia of a rectangle with dimensions b and h about axis passing through each side. So you can actually use this directly, or we can go with this and use parallel axis theorem. They give you the same thing, right? In this example, we saw that we can go from one to another. Just for the sake of practice, I'm going to assume that I don't know these two, and I only know the area moment of inertia about the center. And I want to just use parallel axis theorem, again, as a practice. But you already know them, so you could use AX, IX, and IY. All right. So let's just, for the sake of practice, say I, and let's put the axis in the center. X prime, Y prime. And this distance would be dy. So you have I bar x prime. We know that from the table, I bar x prime is 1 over 12 bh cubed. So 1 over 12 bh cubed will be 1 over 12. B, the width is 100 millimeters. H for this table is 150 millimeters. So that will give you a moment of inertia about x prime, the axis passing through the center. That will be 28.125 times 10 to 6 mm4. Now, what we need to find this area moment of inertia about x-axis. X and y coordinates are the coordinates for the composite area. So everything should be about those axes. In this case, only x, because we're finding the only moment of inertia about x-axis. So Ix for this, for rectangle, would be Ix prime y plus a dy squared. All right, that'll be with area being b times h, which is for rectangles 100 times 150, right? And dy being just that distance, which is still 75 millimeters. mm squared. This is m. This is area. So mm squared. The result, you can find your AX as 28.125 times 10 to 6 plus area, which is 100 times 150 plus dy, which is 75 squared. That'll give you Ix as 112.5 times 10 to 6 mm4. Right. This will be your Ix. Now let's call this Ix circle and Ix rectangle. Ix rectangle, Ix circle. Right? So now you know moment of inertia for both about x-axis. All that's left is to find the moment of inertia with x-axis for composite area. You subtract the moment of inertia with x-axis for circle from the moment of inertia about x-axis for rectangle. So for the composite area, you get Ix is equal to Ix for rectangle minus Ix for circle. You have both numbers. You'll get Ix as 101.15 times 10 to 6 mm4. So you have the table and you know parallel axis theorem. That's what you do. When you have a composite area, you find out how can you break it into simple shapes, the shapes that you have the information about in the table. Oops, in the table. Right. Then for each segment, you find the moment of inertia about the set of axes that you have for your composite area. Right. So typically from the table, you have moments of inertia about the axis passing through the centroid of that segment or that simple shape. So you have to use parallel axis theorem to find the moment of inertia about the axis that you are trying to find the moment of inertia about for the composite area. Right? And then eventually at the end, once you know the moment of inertia for each segment, if it was a cutout, you subtract that. If you were adding multiple simple shapes to form a composite area, you just add this area moment of inertia or moment of inertia.